Okay, so this is the optics, and I want to correct this so we'll start. Now, if you check the syllabus, I made the same mistake on all of them. Look at my office hours on Monday. Turns out I'm not going to have office hours here at 8:30 p.m. That's just, I'm not going to be here. Sorry, that's the typo. That should be a.m. So I'll be here at 8:20 to 9:10 a.m. on Mondays. The way my schedule works is my Mondays are all really kind of all messed up. I start at beginning classes at 9:20 and I finish at 4:10. And so probably you're not going to get hold of me on Monday in general. Uh, the other thing is that I'm teaching most classes in the morning, and so my mornings are almost all booked. So if you need to get in contact with me, it's probably going to be in the afternoons. As far as for those of you who haven't had me for upper level courses, which are probably only you three here will useful. The thing I do a little bit differently in the upper level courses is I have what are called daily homeworks, which are not every day. But there's a point I want you to basically, I don't want to wait for a week for the homework assignment to come in. I want you to actually do it immediately so I can check to see if it's correct. Our first daily homework is actually not due next class because we're probably not going to finish the derivation. So what I'm going to do is this one's going to be due on Wednesdays. And I'm going to do a problem in one direction. I'm going to do the case of a wave moving this way. You're going to do the case of a wave moving along the x-axis, but it's going to be the same idea. And so that's what you're going to be doing in this assignment. And as far as a textbook, there are no textbooks, but if you look on here, there's actually, they got a grant for doing this. There's actually the physics department at Brigham Young University in Utah. They actually got a grant to make an online textbook, which is actually quite good. It's free. If you go here, you can actually download it. And this is actually the first chapter of it. Yeah. There's going to be some details in here we're not going to go over because we have a whole other class where all those details can be developed. And so, but I think sometimes people like something to just hold on to kind of look at stuff and to read. And so that's what we'll have. So this is the first chapter from that textbook. But you want to download it. It's actually quite good. I'm actually amazed at just how good it is for a free online source. If there's no questions, we'll start. Let's start. Okay. Let's start with a wave. What is a wave? What's a wave? Close. Okay, there's going to be some disturbance that's going to transmit energy. And when that energy is transmitted, somehow you can actually use that energy that's being transmitted to do work. So a wave is going to be some disturbance that transmits energy. And work can be done by this transmitted energy. And I don't know why this reminded me of this. I should have said something else at the beginning of the class. The reason we're meeting in here is so I can record the class a lot easier here. The room I was in, for some reason, I was losing videos when I was recording in there, and I don't want that because there's two people who can't attend on the Monday class, and so I can't afford to lose lectures. Yes.
Is every class going to be in here? Just
no, because here's going to be the complication. The complication is that on Tuesday and Wednesday, meaning next classes, we're going to be in 202. So Monday here, and then on Tuesday and Wednesday, 202. In other words, you have physics 125 lab. Okay. Just because I can record in those rooms easier, and they have really a lot of nice blackboard space. Okay. Now back to the class. Okay, so this is what we're going to have here. And it turns out there's going to be a differential equation that you're always going to have whenever you have a wave. And I want to show you basically how this differential equation comes. So we will show that waves are described by partial, well, by the wave equation. Which sounds stupid, waves are described by the wave equation. Really, imagine that. By the wave equation. Which is a partial differential equation. Okay, this is one of these equations you just want to memorize it because you're going to see it as soon as you see it, you know you have a wave. The way it's going to look, it's going to be 1 over v squared, second partial of y with respect to t, here, equals here. There's going to be anything of this form here. This v here, v is the velocity of the wave. Okay. The y here part, this is actually the thing waving. Remember, if I have like a wave like this, the y might be like the height of that wave moving like this. The y is whatever the thing moving. And this is the thing moving. We're going to find out for the electromagnetic wave, it's going to be the electric field or the magnetic field. And this x here, this is going to be the direction of motion. This is direction of motion. Now we're going to actually have a more general version of this. This is going to be replaced by something called a Laplacian. Don't worry about that yet if you don't know what that is. But this is going to be right here. This is going to be a one-dimensional version of this wave. What I want to do is I'm going to give you a remarkably simple, but also remarkably subtle derivation for this. And then what I want to show you is basically that whole class we took called 126. There were 4 main equations we had. What were those 4 main equations called? Maxwell's equations. I want to show you that I want to use Maxwell's equations to show you that if you beat on them, you get this for the electric and magnetic. Okay. So first of all, I want to give you a it's not hard, but it's also it's kind of a little subtle derivation of this. So a subtle. And I better mention what this is. This goes out of focus periodically. A subtle derivation of the 1D. This is a one-dimensional equation. 1D wave equation. Okay. Okay, you're going to be deriving this wave equation like from a whole. Every time we have like a new system, we're going to end up with kind of a new wave equation. You're going to be doing these derivations throughout the whole semester to the point when you're going to have no problem deriving these equations at the end, and you're going to know exactly what to do. There's a beautiful way to approach these things. Okay, so let's draw a little matrix. So let's say here's a little wave with some little pulse. It doesn't matter what it is. And it's going to move this way here, some velocity v. This is at time t. Well, hey, what's going to happen a little bit later on? This wave is going to move. This wave is going to move over to something like this. So this is basically at t plus delta t length. The wave moves. Okay, the derivation almost stops at that point, and clearly you have to have the wave equation. Okay, there's some details for you. So what I want to do is I'm going to kind of amplify this little section. So draw this section larger. So I'm going to draw that little section. Remember the first time I saw this derivation, I went, oh, that's so slick. This is really cool. So we draw that little section here where I have kind of like this part. And then I have like this right here. So this is that T, and this is that T plus delta T. And I'm going to look at this little section here. So I'm making a triangle like this. Okay. What would this distance right here? So this point here, if I draw X here like this. This is a point X. And this point over here is X plus delta X. So that means that this distance right here between here, this is delta X. Right? And so then I can look at this section right here. I can call that delta Y. Right. Now suppose I want the slope at time t. So the slope of the line at t is what? I want this slope right here. What I do, I said that this is delta y over delta x, and this is at time t. Right? Okay. So I'm going to put this here. This is delta y at t equals. Okay. Well, what would that delta x have to be? This wave is moving with a velocity v. V times delta t. Right, so the delta x here has to be v times delta t. That makes sense? Here's where it gets a little on the slow side. If you're here, so this is y, let's say this is the y-axis here, this is y at t. This right here is the point y at t plus delta t. And this is all at the point x plus delta x here. Okay. What would happen? The point starts here, and then it moves down to here. Okay. What would that delta y be? Would that be a positive or a negative value there? That'd be negative. So I would have minus delta y here like this. And this is going to be right here. I'm sorry, I have to put a minus sign in here. Just a second. This delta y occurs at x plus delta x, and it is the delta y from t to t plus delta t. Now this right here, this is positive. This whole side here is positive. This side here, this is negative. This delta y is negative. So to actually have a positive value become a positive value, I need this minus sign to get them to be the same. Does that make sense? Okay. Hey, what happens if I let this delta t become really, really small? This delta t becomes really, really small. What happens to my delta x and delta y? Really small. They become really, really small. But this y here, y, is a function of both x and t, right? Y is the height this way, y, right? This is x. The height of this, whatever, unless it's a string or whatever, is going to depend on where I am along the x-axis, but it also depends on when that wave is moving through. That makes sense? Hey, then what does this do here? Here I'm seeing how y is changing, basically at a fixed value of t. Well, with respect to x. What does this become in the limit? Is this delta x and delta t become 0?
Y with respect to
What kind of
time
derivative? It's a partial derivative. Okay. That means that if we look at the limit, that this delta t delta x go to 0. Since this y is a function of both x and t, right here this is at a t value. which we're at we're at this, we're right here at a fixed side of t. This side here becomes the partial of y, with respect to x, equals -1/v. And then what does this become? It's that's y over v to t. Now I'm at a fixed value of x on that side, so that becomes a plug it so.
Partial derivative dy dt.
Exactly. That's from a partial of y with respect to t. So what's happening here, I'm at a fixed value of x. The x value is fixed. And what's happening, the y is moving from here to there. Okay. Okay. It's gonna get subtler. It's not gonna happen, it's not gonna happen. What assumption did I make about the shape? That curve? Two-dimensional. Well, sure. What form, mathematical form did I use for it? What did I say it was? I didn't say. Okay, I made no assumption on what that curve is. Meaning it doesn't matter what this y is, therefore, I'm actually have a differential operator which must always be true. Since no assumption was made on the actual form of y. The differential operator, the differential expression, what I say operator. Then you can move over. Partial with respect to x equals -1/v. Partial with respect to t must be true. What does it mean to be an operator? You three are familiar with that term. Those three are them. Those four now.
The mathematical property that acts on another object.
Yeah, so this right here, this has to act on something, it has to act on another function, in order for it to be something. That's what it means to be an operator. It'd be a little bit like saying d by dx. That would be a differential operator here. Why? Because what? This by itself, you can't do anything with it. It has to act on an f. Okay. But if you leave it like that, then you refer to it as an operator. And since I made absolutely there was absolutely no restriction on what this y is, that means that the differential part here. Okay, must be sorry. Must be true. Okay. I mentioned that this is so. Okay, so what I'm going to do, I'm going to let that act on this again and Shazam, I have the weight equation. So let this act on this. And if we do that, what happens? We have this here. With this guy here, with my wife here. And this guy is over here. What am I left with? This acting on this is the second derivative. Minus sign swell, 1/v, 1/v gives me 1/v squared. And that gives me this. Very, very slow. That's actually the hardest derivation to do this. Probably is no. Okay, the only reason for doing this is I wanted the. Okay. Again, there are other derivations and you're going to see them all. That we're going to get for that. But this one I can do it quick. Okay, let's stop at this point here. Are there questions with that? Ask away. I know you want to, it's the first day. Do we need this the first day of class? Really? On the first day you give us this derivation? Okay, what are we going to do with this? What I want to do, I'm going to spend today and the next class. I want to show you that Maxwell's equations are going to give you the same thing. So we will see, and this is a basis for optics. Real and LC. Now, sure. That Maxwell's equation. Will give something like this. Okay, I can see this. Yeah, no, there you go. I'll put it as equal like this. So you might get that for the Z component of the electric field. And I might get something like this then for the Y component of the magnetic field. And what do these look like? C is what? It is the speed of light. Speed of light. So what I do, when I show you that Maxwell's equations are going to get things like this, meaning that the electric field is going to travel like a wave. It's an equation like this, meaning the magnetic field is going to travel. Now again, we're going to run a more general fashion. But what we have right now, we have to do a little more restrictive than what we do. Does that make sense? So what do we have to do right now then? We need to review Maxwell's equations. Okay, so let's do a review of Maxwell's equations. And then let's actually see that they give rise to that. Let's review. Maxwell's equations. Okay. I'll start off by writing one. You tell me what comes after the one. What's the first Maxwell equation we had in 126? Gauss's law. What is Gauss's law? So I'll start off by writing Gauss. Okay, there's a question of basically how many S's should this have? Where does the apostrophe go? In this course, it's going to go there. It comes up there's S. I mean, there's two. I've actually heard that I've heard actually a strong case is that there should be 3 S's. It should go after 1 SS. But that just looks stupid. So, okay. And that's all we're going to discuss for the rest of the semester. It's basically we're going to have open debates on how many S's should there be in Gauss's law and where the apostrophe should go. We're not going to learn anything about optics. But we all know how to spell Gauss's after the end of the semester, which is the important. So what is that? We have an electric field. It's just like this. Okay, then we construct what kind of surface? This closed surface called a Gaussian surface. So this is a closed surface here like this. This is a closed surface. And we specify something on the surface of that instruction. What should we specify on there?
A little keep mostly.
Yes, for the area. So we drew a little area vector here on the surface here. We call that this dA vector. So this is the area vector, the area vector. What's the D mean again? D always means some small amount. Tell me about that dA vector. By definition, it does what?
Point normal to the surface.
So always has to be normal to the surface and this closed. The dA is perpendicular to the surface. And one more really important point. Outward. So if I drew the little dA vector down here, how the little dA vector here has to go? Path. We defined then the electric flux. How do we define the electric flux? Okay, that's going to be the total. Okay, that's going to be the actual ball. How do we define any flux from the point of view?
None of the electric field that leaves the Gaussian surface.
And how do we do that?
Integrate across the surface.
We need something. Let's start right here. If I want the flux, here's my E. I want the flux at this point here to this dA here. By definition, the flux going through that little patch of dA as well. I'll call P as flux. I'm going to say the D feed flux through that little thing here is what? It's how much of that E points along the dA vector. So if I want to know how much of E points along the dA vector, what do I have to do?
Dot product.
A dot product. So this has to be E dot dA. This is how much of that E points along that vector there. Make sense? Now, if I want to fit through the whole surface, what do I have to do? How many integrals are there? On the surface. It's on the surface. It's on the surface. Okay, it's not 3. It's not 1. 2. Okay, so it's a two-dimensional we have to go over the whole surface. So what do we have to do to this? Yeah, we have to put that little loop like that. That means over the whole surface. And Gauss's law states that what? That this is directly proportional to the electric charge enclosed in the surface. So the electric charge is Q enclosed in the surface. And what's the proportionality constant? One over epsilon. Well, actual Gauss's law. Is this? What's your epsilon column? Is the permittivity of
A vacuum.
of free space, which is the vacuum of free space. Okay. So this is Gauss's law in integral form. Hey, we have Gauss's law in integral form. What might there also be? Gauss's law in differential form. It turns out we're going to spend a lot of time figuring out how to write that in the differential form. It turns out that's going to be the way you deal with it. So this is Gauss's law. In this case here, how much charge would there be? And that my little cartoon picture.
Yeah.
It would be 0. So what would be the net electric flux going through that surface then?
0.
0. Okay. Gauss's law, first one. Now, I can actually replace this electric field. I could put a magnetic field there. Just as soon as here's a magnetic field. Here's my closed surface like this, and I could ask, what is its flux? The magnetic field. What's the flux of the magnetic field? with this surface. What did we find out about this one? This is always zero. This is always zero. Now, what's the name of this equation?
No magnetic monopole.
Meaning it has no name, but that's what it means. Okay, the equation has no name, but the implication is what? That there are no magnetic monopoles. So this is nameless. The implication of the statement is magnetic monopoles do not exist. Am I still on the board? I am, and I'm still clear. Good. What's a magnetic monopole?
One point that emits magnetic positive and negative.
Yeah, so if I had just a pure N pole like that, what would a pure north pole look like? Yeah, the B fields would be coming out like this. That'd be a pure north magnetic monopole. A pure south magnetic monopole, the lines would be coming in like this. And if I were to construct a Gaussian surface like this from here, this would actually have a positive flux, right? This would have a flux, which is positive. If I were to construct a Gaussian surface here, this would have a flux. That's negative. The fact that this is zero, what does it mean about these two bubbles here? They don't exist. Okay, that makes sense. So if I have a bar magnet, if this is a north pole, if this is a south pole, why would that then have no magnetic flux if I construct a Gaussian surface around this?
You can look this out.
Yeah, so the top was happening, the fields are coming out, so I'm going to get a positive dot product. Here the B fields are going in, so I'm going to get a negative contribution. And then those contributions are always. Okay, so I have two of the Maxwell's equations. Okay. If you ever find a magnetic monopole, guaranteed that year you're going home with a Nobel Prize. Guaranteed. Your Nobel Prize. Now, there's a very famous physicist. I would actually argue. I'd actually put him just a little bit ahead of Einstein. His name is Paul Dirac, and he postulated the existence of these, and you only need one. And he said, what happens if you had a magnetic monopole interacting with a charged particle? Well, he was able to show through this brilliant argument. So I think it was brilliant. Said if you do that, then electric charge has to be quantized. So you can say, well, where's this magnetic monopole? Oh, it's way over there in that part of the universe that you can never get access to. So you still have this true in 99.99999% of the universe. Okay, but then you also don't have charge quantized. Okay, and so people have spent long times looking for these things, and they often look like stupid objects often, and it's just like, really, why are you doing that? Okay, well. Okay, give me another one. What? Ampere's law. Okay, I'm going to do that one last because of something, but you're correct. Okay. There it is. Okay, so let's kind of go look at this one here. So here's my E field. And this right here, this is a loop. It's not a closed surface. Okay. So even though it looks like a closed surface, it isn't. Now what do? We draw something tangent to that loop. We call this DL. So this DL here is tangent to the loop. Like that. And we're going to go this way here. And it's actually just a tiny little piece of that loop here. So this represents the length of it. It's some little tiny piece of that loop. And it's always tangent. So over here, the DL's like this. Over here, the DL's like this. We're going to look at this quantity here. If I'm up here, here's the DL. I'm going to look at this quantity E dot DL. So I'm going to say how much of this E lies along that DL. And add that up along the entire loop. So how many integrals would that be? 1. Good. Okay, now from general physics, meaning second semester physics, This looks a lot like a voltage. Right? And so this right here, we actually call it EMF. Which is basically, it's like a voltage. I'll make that point more clear when we get to that point. I just want to leave regions. What does EMF stand for?
Induced magnetic,
Close.
induced magnetic field.
Electro. Motive. Force. Electromotive force. Okay, but it's basically a voltage. And what did we say that this equals? Minus d phi b dt. And what is this phi b? This is your magnetic flux. That doesn't say magnetic at all. Magnetic flux. Hang on, I just thought I told you over here, your magnetic flux is always zero. So why is this always zero? It's not a closed surface. So what you have here, oh, I need to do it for phone, sorry, that always sense, yeah. So here's a closed surface. So if I have a B going like this, if I have a B going through a closed surface here, I do a little dA, I dot my B into dA. If I do this over the whole surface here, that's always equal to. Now, if it's like this, we're now this right here, this loop, I'm integrating along here. Here's my loop. I'm now looking at the flux speed. Okay. It is not close. Okay, that's why it's not zero. Does that make sense? Okay. And so what do we call this? This is Faraday's law, which means what? That if I have a magnetic field that's changing with time, I can actually produce an electric field. Okay? Questions? Now, this is the last one. Charlotte already mentioned it. That's Ampere's law. So what is that? Well, we're gonna have a magnetic field like this. And here's my loop. And here's my DL vector, again, goes like this. I'm gonna look at this quantity here, this B dot dA. Okay. What does Ampere's law say?
Magnetic field can produce an electric field.
Okay, let's get the expression that what you're saying is going to be true. Yeah. What was the first version we learned of this? We said that this was directly proportional to how much charge is coming through. So it says, I'll put this in here. Okay. Meaning what? Let's say here's a wire like this. This is a current. This is wire carrying current out of the page. In other words, imagine I have wire like this. From your right hand rule, how does magnetic field go? Good review of physics too. You point your thumb in the direction the current goes, your fingers wrap in the direction of B. Right? So you're going to have a B like this. Make sense? Now, if I would have a loop, here's my loop. So here's my DL vector. What's going to happen here? Here's my B, here's my DL. I'm going to have some value here. If I increase my current here, what would happen to the magnetic field here? Increase current U, increase the B field, right? So what this is saying here is that if you have more, this is a current basically, it's a current poking out through that loop. That's what this line close means here. That if I have more current coming out through this loop here, I increase my B. If I increase my B, I increase this in quantity. Now, what is that proportionality constant given by?
Newton.
That's Newton naught, which is the
Permittivity.
permittivity is going to be the epsilon naught. This is almost like a permeability of free space. So permeability. Free space. Okay. Now, this is where things were fine. And then Maxwell came along, and then Maxwell realized this isn't quite right. What was Maxwell's contribution to this?
Isn't it that like if you have two parts of a wire and they're like disconnected, according to this, that disconnected space would have no B field whatsoever, where there really is a bit of a B field there.
Well, so what did he do? Everything you said is true.
Um,
He imagined another current cloud displacement. And we're going to see explicitly why that comes in here. Maxwell's contribution. So this is before Maxwell. Uh-oh, am I off the board? I'm not. What Maxwell's going to do, it's going to come along. And it's going to do the following. He's going to add a new term here that he calls a displacement. Okay, today I'm just going to put this in here. A little bit later on in this course, I'm going to show you exactly why this has to be here. I'm going to give you the real derivation. There's a reason why this term has to be. Okay, this displacement term. And I'm just going to state what it is for. Again, I'm going to prove this later on in this course why it has to be there. Well, Maxwell it was proved that this is going to be epsilon naught dphe dt, and this right here is your electric flux. This is through the loop. Okay. Now, a very modern way of looking at it is this. This is Maxwell did not use this argument, but this is a modern way of looking at it. It's a symmetry. Look at this. Okay, what does this state? This states that if I have a magnetic field changing with time, what do I produce? An electric field. Okay. Then by symmetry, what might you expect? If a changing B field can create an E field, then by symmetry.
Creates a B field.
A changing B field, you'd expect to, a changing E field, you expect to create a B field. And that's what you have here. Changing E field with changing with time is now creating a B field. That's a very modern way of looking. That's a very symmetric way. That's not what he used. He had the British, he was Scottish, and the British had these, they're very good model builders. And they had this bizarre mechanical view of the vacuum gears and everything like this. He took that picture series. And if you take that picture series, you end up getting that. Okay. So those are the equations. What I want to show you is that if we use these four equations, we're going to end up with a way. Okay. And that's what we're going to do today. Then you're going to modify the little argument to basically do what I've done here, but basically for a different, a way for you in a different direction. Okay, so let's do this. I'll start it today. We'll finish it tomorrow. So let's use Maxwell's equations to prove that prove that that let's say to prove that Maxwell's equations. That's really a remarkable. Let's grammar need not speak, need not good. Bad. Okay. Yeah. Okay, so let's show that Maxwell's equations Okay, here's the wave equation for the E and B. Okay. That's what I should. Okay. So here's gonna be our, okay, so I'm gonna do this in, I'm not gonna do the general case today. I'm gonna do the general case when we get the differential forms. When we have the differential forms, I'm gonna show you this in extreme detail. It's gonna be beautiful. But let's start there. So here's what we're gonna do. Let's assume that E is initially in the Z direction. So further, assume we are in a vacuum. So if we're in a vacuum, what do we know? What does that mean? What does it mean about the charging closed?
Yeah.
Yeah. What does it mean about the ion closed? That's also true. Let's go through this. Yeah. Like. Never somebody swing, but seriously, I always want to start saying just random. No, it's just people is it was the nicest guy. I inherited my father's very inappropriate or something. Okay, so let's start off. So here's my E field like this. Get a little closer. So here's E. This is in the Z direction. Okay. And so this is going to be at some point here like this. This is at the point, this E here. This is E. Yeah, it's a function of X, like the same. This right here is Y. And come over here to this point, which is Y plus delta Y. And go up to here. And here's another E. You're going to see that this is E. Same value of X. Doesn't change X value. I've changed the Y to Y plus delta Y. Z hasn't changed. So as soon as I have that, I get the big. Well, you could say how. Well, let's find out. Less than following. Previous losses. Okay. So what I'm going to do, I'm going to redraw the picture over here just to make it a little more user friendly. So this is here. This. So this is going to be this is E, next one is Z. This is E, this is X, Y plus delta Y. This is Z. This value here. That's delta Z. This value here, delta Y. And I'm going to integrate. I don't know. I'm going to integrate like this around here. You have to do that. I'm doing a right hand rule on this. Okay. So, what does that become? How many terms would that? What does this mean here? What does that mean?
All of the individual pieces combined.
I'm going all the way around here like this. And what is that DL? It's always tangent to that loop. Okay. So this is going to really break into 4 pieces here. Here's piece 1, 2, 3, 4. So we have this guy. It's this guy. Another one. And this one. Why don't I have a little loopy thing on these?
Because that's the individual part, it's not.
Yeah, it's just a section, there's not the whole loop all the way around. Okay, what does this section think to be and why? If I was, it has to be 0, what would that dy have to be here? I mean, this DL.
Perpendicular to.
So this DL would be what? This DL would be dy j. Okay, well, what do I know about that E compared to this guy here?
See that?
Is 0, right? This right here, the E is perpendicular to y. Okay, that term goes out to 0. Which other piece can I kill? I can then also kill 3. So likewise, this one here, this E perpendicular, this dyj. I better do this. Okay, let's look at section 2. What's a section 2?
It is 410.
What?
It is 410.
The clock was against me last year too. It's still against me. It was against me this one. Okay, technically, I guess the class is over. Okay, so we'll beat on this piece and beat on this piece and see what we do. Okay. Have a good day. I'm still clear. That's good.